All right, 10th grade. Here is lesson number 3, Newton's law of gravitation. Your data from last class, the lab you did about recreating Galileo's lab on gravitation, we're going to analyze it together using regression next class. I want to be there to do that. If I'm not back next class, I'll put off another one. But I'm hoping I'll be back on Friday. We'll see what the doctor says tomorrow. So here's the tone for today's lesson. It's a one-pager. You will definitely be using one page, if not 2 more after this for practice problems. I said earlier, it's really important you do the notes and the formulas and explanations on a concept and practice problems right after that in your notebook. So when you go back to review, they're all together. So one-page template. We have Newton's findings, what he did, how he found it, Cavendish Experiment, another third of the page with a drawing of his apparatus and what he did, and then the actual law of gravitation and how we look at that here as well. Okay, this is our second formula of the unit, and it is a longer formula than the first one. So pause the video and draw your template. Okay, so now we're going to talk about how this knowledge about gravitation has progressed across multiple generations, multiple scientists over time. We go all the way back to Aristotle. So Aristotle is one of the more famous Greek philosophers, and they're called philosophers, not scientists, for a reason, because they didn't really do experiments. They did what are called thought experiments, where they thought about something and they looked for observations of daily life, the world around them, that would kind of explain what they were talking about. So, for example, if you're thinking about gravitation, you might look at objects falling, birds flying, and try to kind of have a conclusion based on what he's seen. But he wouldn't actually design an apparatus, collect data in a controlled manner, and then analyze that data the same way that Galileo did or Newton did. Which is why a lot of the times the things they said were incorrect. They were kind of common sense or logical explanations, but oftentimes there's forces at work that we cannot see with the naked eye. So what Galileo did when he was working on motion is he looked on how objects fall, as we know from our last lesson, and proved that objects all fall with the same acceleration on the same planet, and that disproved Aristotle's idea. Aristotle thought that objects fall at a speed proportional to their mass, which is what a lot of people who don't know very much what physics think, that the heavier an object is, the faster it's going to fall. And that is not true in terms of acceleration of that object, but we do know that mass has to do with the force of gravity, of how strong the force is, but the acceleration of gravity is the same on Earth, no matter how much mass an object has. So Newton then analyzed the relationship between the mass of objects and the force of gravity. So he took what Galileo did, saying it's a constant acceleration, and then said, okay, their mass has some role to play in this, and he looked at the relationship between them. And he did this using data from lots of different astronomers and scientists, up to natural philosophers, collecting data on the planets and the moon and the stars, and he used that data to look at how mass affects gravity. And this all kind of began, the famous aha moment for Newton is, of course, he's sitting under an apple tree and an apple falls on his head. Now, this story may or may not be true. The best explanation from scientists is that it's not true, and that it was, so it started out true, and then Newton elaborated, basically. So the idea is that he started out telling the story because he was probably sitting in an apple orchard. We know that his family house in the UK had an orchard, and we know that he used to go there to think quite a bit. And from what we can tell from letters written by scientists at the time, that the first kind of story of this, or the first entry of this, is him writing a letter and just saying how he was sitting in the orchard and saw an apple fall, and inspired him to look at gravity a different way. And then as many stories get with the retelling, Newton's tale got more and more kind of interesting, and he added the fact that, wait a second, I was sitting on a tree and the apple fell on my head, is where it kind of ended. But different naturalists to the time, like his colleagues, have all said that the story didn't really start out that way. It found some different letters. So, like anyone, Newton is prone to hyperbole and kind of making his story sound even better. But what came of this apple and tree thing, which may or may not be true, is that he had a goal, and his goal was to quantify, put mathematical relationships to how gravitational force made different objects behave. So he wanted to take from just the description of the relationship and acceleration is the same of all objects and actually put a number to it and an actual mathematical relationship to it. So what he did is Newton looked at first at mass, and he knew already that F equals ma, which we learned about last class. Force is mass acceleration, so he knew that the mass is going to affect the strength of the force. And we knew from Galileo that acceleration is constant due to gravity on the same planet. So the next thing you're going to figure out was distance. So how does the distance between objects affect the force of gravity? So what he was able to deduce from all this data from astronomers and looking at different patterns between orbits of planets and different kinds of data on the orbit length and between celestial objects was that the distance, the forces depend on the distance, and the distance between those two objects squared specifically is what he was looking at. And then his next step was to consider the mass of the objects. And what Newton realized with the mass of the objects is the larger the objects were, the more massive the objects were, the stronger the force of gravity was between them. So look at this little image here. This is showing you how distance affects gravitational force. So gravitational force measured in newtons, like any force measured in newtons. So if the apple's weight or the force of gravity on that apple is 1 Newton on Earth, if I move 2 times that distance away, the apple now weighs 1/4. Its force of gravity is now 1/4 what it was before. And then 3 distances away, 1/9, 4 distances away, 1/16, etc. So this is what we call an inverse square relationship, where the force due to gravity, which we know is Fg, is proportional to, so that still means proportional to, which is this one changes, the other one changes in the same way, 1 over distance squared. So we call this an inverse square, and it's an inverse because it's 1 over. Okay, it's not directly proportional, it's inversely proportional. And it's a square law because we're talking about the square. Distance is squared. Okay, so he knew that as I increase the distance, the force will decrease at an inverse square proportion. And we know from our last lesson that gravitation is the weakest of the fundamental forces, but it works over infinite distances. So we had that information, he figured that out from all the data from astronomers, and he looked at the masses. And so he figured that the larger the masses are, the stronger the force of gravitation. This is a really cool diagram to help you kind of look at these relationships. So if I have, here's my kind of standard, where I have 2 different masses, and there's a distance d between them, and the force is just F. So these are all directly in proportion here. If I increase the mass of one object to twice what it was before, the force is now twice as strong. If I make the mass 3 times as much on one object, the force is now 3 times as strong. If I make the mass twice as massive on both objects, my force is now 4 times as strong. So these kinds of patterns is what Newton was analyzing to find this relationship. If you were to increase the distance, double the distance, the force is now 1/4 of the strength. It is twice as much, but the inverse of, so it's inverse squared. 2 squared is 4 over 1. And then if I was to half the distance, it's now 4 times as strong, because if I take a half and I square, 2 squared is 4, and now I inverse it, so it's 4 over 1 instead of 1 over 4, I have 4 times the force. If I increase both masses, doubling both of them, and increase the distance by double it, this will equal out exactly, and I end up having the same force. So if you want to take physics in the DP, being able to understand the relationship between variables like this is super key. Okay, and if you, even in this class, if you're able to understand these kind of relationships, just memorizing formulas and putting numbers in, you're going to understand everything so much better. It's worth taking the time to study these relationships and look for the patterns. Okay, if this does not make sense to you relatively easily, the DP physics might not be the choice for you for next year. We can definitely still talk about it, but just some people, physics makes sense to, a little more easy than others. For me, it depends on the teacher how much it makes sense to, but luckily Mr. Meyer is a really good teacher. So to look at this image and use it to kind of help you look for the relationships, okay? So what Newton's obviously led, and the calculations that he had all done with all this data from astronomy, is that the formula that he had is this kind of early draft of the formula, where we have force of gravitation is proportional to, that kind of fish-looking symbol means proportional to the product of the two masses, so mass 1 times mass 2, divided by the distance between them squared. Now, what Newton realized is that this force had to be very, very weak. If the force wasn't weak, then the objects would be attracted to each other and moving all across the space in kind of crazy ways. So he knew his formula as it was wouldn't be accurate. So he added a constant, and the constant was G. So here's G, it's the universal gravitational constant. And he did not know what this was. He had no way to calculate what G was going to be, only that it would be very, very small to make everything else work in the correct proportions. So this is your formula for Newton's universal law of gravitation. But we talk about another scientist who figured out what G is. And that is Cavendish. So about 100 years later, we have Henry Cavendish, who took on this problem about the value of the universal gravitation constant. And he did a very time-consuming, like months and months and months of work on this experiment to calculate G. And Newton was right, G is very, very small. This is the value of G, 6.67 times 10 to the negative 11 newtons per mass squared per kilogram squared. Now, you don't need to memorize this number. You need to have it in your notes. You can refer to it in your practice problems and calculations. I will give it to you on a test or quiz. We need to know what it is and how to use it. Okay? Now, this is what Cavendish did. A big part of the DP science we've been working on as well since grade 9 is understanding how scientists come to conclusions, the processes they do, the experiments they do, that kind of stuff. So Cavendish's experiments are really interesting to look at. So he designed this giant apparatus. This shot the size of like a small house. Okay, it's a really, really big apparatus. It was in a kind of a garden shed on his family property in London, and it was huge. So he had two very, very large lead balls and two very, very small ones that were close to each other. And what he did is he suspended the balls, so the big ones here are hanging down from a center frame that allows them to move, and the small ones here are also hanging from that allows them to move. Here's a kind of similar setup. We have the two small ones and the two big ones, and they are all able to rotate and move around. And he could see how they're going to be attracted to each other based on their gravitation, because they're free to move and they're hanging in a very controlled environment. So what he did to observe this observation is he put a mirror in the middle, and the mirrors in this one are right up here, and then he could see as the string spun, as the small ones kind of spun around, he could look for the reflection of the light. Now when he did this, he used candles on each of the telescope pointing in to then measure the angle of reflection. So he would look at the distance from very far away. He would look at it to kind of see, okay, I set it to start here, kind of let it move, and he'd measure the angle reflection of the light. He did this so many times to get it right, and it took many, many, many trials with data. The reason why he had to do this from a great distance and using the reflected light to help him figure this out is because if he got too close, his own gravitation would affect the findings. So he wanted to make sure that everything was constant. There's nothing here affecting the gravitation. Everything is immobile. Everything's still except the balls can move. And so if he was there and he was moving around, which he wouldn't be in the same space the entire time, that would affect the experiment. So hence the telescopes to see the light. So you need to draw this in your notebook. You're expected to know this kind of procedure for methodology for an experiment like this. So you can draw either the big apparatus or the small kind of zoom in part of just when this section kind of zoomed in. Okay, here's a video about Cavendish's experiment where he kind of shows you a model of the apparatus and talks about Cavendish's personality, how it came to this. I'm not going to play it with screencast for you. The link will be on Schoology in the folder as well as with your substitute teacher. So you can look at that. But it's really cool. So he explains kind of the context of Cavendish, what his research methods was, and what he did. And it gives you some historical context as well. If I play it for you in the screencast, my time will be way too long. Okay, so this is the form we need to draw. This diagram shows the relationship between the two forces. Okay, so F1 equals F2. These two forces are equal if G is mass 1 times mass 2 over R squared. You can, on your using your formula page, I recommend you also put here an explanation of what all of those variables are. As before, I will give you the formulas on a test or quiz, but I will not explain to you what they mean. So you need to know what these letters all mean. So after many, many years of work, Newton's law of gravitation, universal gravitation, was finalized. With Cavendish's contribution, we have Newton, we've got Galileo, we've got Aristotle, all of them working together, building on their knowledge and each other's knowledge of time after time. So draw the notebook and draw the diagram in your notebook and record the formula. You can do practice calculus with this. If you're not sure how to use exponents like we have here and scientific notation on your calculator, please get help from a math teacher, from a classmate. You can also look on YouTube. Obviously, I'm not physically there to help you with that. If your calculator cannot do exponents, calculator.net, which I linked in Schoology on the unit resources folder, and I'll put it on the update as well, has exponent functions. You can use that as well if you don't have your calculator. No phones, guys. Okay. One last thing here is inverse square relationships. So we told this earlier, and it's a really important thing to understand these relationships in physics. So an inverse square relationship is where one variable, so variable y, is related to variable x, where 1 is equal to the square, so x squared is equal to y, but the inverse of that square, 1 over x squared is equal to y. So this is what that graph looks like, that parabola looks like on a curve. Okay, it's an exponential relationship here. So which part of Newton's law of special gravitation does this apply to inverse square relationships? Well, it definitely applies to the distance, right? Distance relative to mass and force. So force is equal to the inverse square of the mass, of the distance, and mass is also equal here. Okay, so if you got this and you know how to work this, you're great. That's the end of the lesson. You can go with the practice problem sheet. There are 31 problems. You only have to do the first 10. If you don't get it or you want to practice, you can do more. I will have the answers available to you to check your work for next class. Every time you practice problems, you need to check your work as part of the formative feedback for yourself and for me to make sure you're getting it right. Okay? So it's in your notebook. If you need some help with scientific notation, I'm going to do like a little mini lesson on that now, a little reminder, and then you get help with that. If you know some notation and you know how to divide and multiply those kind of big numbers to small numbers, then you're good to go. Just pull up the practicums on Schoology and get it in your notebook. Okay, so for those of you who need it, here's reviewing scientific notation. It's very, very useful with very large or very small numbers. And that is because in science, we have a lot of very small and very large numbers. For example, in biology, we talk about very small numbers in the context of bacteria, and other, like the nucleus or parts of a cell. In physics, we talk about them in chemistry, the size of atoms, of nuclei, of particles, that kind of stuff. In gravitation, what kind of really small or really large numbers might we encounter? Really small or really large? Which ones? It's going to be both. Remember, the gravitational constant, G, is a very small number, and the distances and masses in gravitation are often really, really large, especially if we're looking at planets, which is what we're going to look at a lot because what Newton looked at, and talking about orbits is part of this topic. So when we're reading or writing a number in scientific notation, a good thing to remember is that the exponent on the number tells you how to move the decimal point. The decimal point here is going to move 4 times, and the direction of the decimal point moving is based on the positive or negative of that number. So if it is less than 0, a negative number, I'm going to move it to the left, which will make this a very small number. This is a positive exponent, so it's going to move it to the right and make this a bigger number. Okay, so it's a positive exponent, it's a big number, move it to the right. If it's a negative exponent, it's a small number, move it to the left. Try and find the logic there. Negative means it's small, move the decimal to make it a small number. If it's a positive number, it's large, move it to the direction to make it a big number. Okay, number of places of the exponent. So here's a couple practice ones here. Take these two in notation and write them out in their actual form, and then take these two in their actual form and write them out in notation for me. Okay, pause the video so you can do that. Okay, guys, let's check your work. Did you get these right? If you did not get these right, then you need more practice. You can go online, Khan Academy, you can talk to me, I can help you find some resources, talk to your math teacher, talk to a classmate, but you need to take the onus yourself to find the resources you need to be helpful. If I was there in class today, I would definitely help you in person, but I am not. And this is killing my throat to do this lesson, so I'm not going to be talking anymore. But you can definitely get help, okay? If not from me today and you want to talk to me as a classmate or a math teacher, then talk to me when I'm back on campus. The other part of this to review is multiplication and division. So when we're multiplying with standard notation, we're going to take the two coefficients, the 2 and the 4, and we'll just multiply them. So 2 times 4 is 8. And then we're using exponent laws from math to take my two exponents, 10 to the 4 and 10 to the 2, and I'm going to just add them up. So 4 plus 2 is 6, so 8 times 10 to the 6 is my final answer here. Then dividing them, I'm going to divide my exponents like a normal division. 4 divided by 2 is 2, and I'm going to subtract the exponents. So 10 to the 2 and 10 to the 4, subtract them, 2 minus 4 is negative 2. So that's all you need to know how to do to use this formula for standard notation. If you need more practice, you need more help, please get resources. Go online, talk to classmates, talk to me, talk to a math teacher. You need to get this stuff sorted, okay guys? We're here to help you. Okay, so your homework is the first 10 practice calculations. If you need more practice, keep going. I will have the answers for you next class, and you can use them to check your work. Every homework is a formative, so check your work every single time. Because you don't know if you're getting it right or wrong, you're not going to know if you need help or not. Okay? Hope this is helpful for you guys, and have a good one. See you later.